Hello everyone, I am Muhammad Asif, and today I am going to present one paper that is recently published in almost in this month in Science, which is a top leading journal in the world. And this research is basically unique from its point of view because they use very ordinary material for the capturing of carbon dioxide for a long time. From the title, we can see this is the building materials could store more than 16 billion ton of carbon dioxide annually. And we know nowadays carbon dioxide emissions is around 37 gigaton. Uh, and now if they can capture about 16 billion ton, they can capture up to 40 or 45% of CO2 emission as of the 2025. So this is a very promising materials. So today's topic maybe is very interesting because of several reasons. So first, we can learn from today's talk like how we can do high quality research without advanced resources. So this is one of the biggest challenge for the developing country like Pakistan and other countries. So we do not have enough resources and which are main hindrance for our high quality research productions to for either high quality publications or a high quality some research outcome for the industrial purposes. So this is one of the biggest challenge that we can address and we can somehow we can learn from this paper from for today. Second is how to make an idea for a high impactful journals. Like this is also a very important point to discuss like how we can go for the high impactful journals. This is maybe useful for the many of us because this is a dream for every researchers to publish in a such a prestigious journal. So maybe I will try my best to explain how we can get an idea based on their data and their research questions and problems. And third is how we can do a research that would be world recognized. So we have to discuss like how we can do a research that is recognized by the world because many time we do the research that is basically localized and that's only be beneficial for some countries or some portion of the countries or even in a limited area, so that may be not get that much recognition in the world. If we consider all world scenario, that may be beneficial for us to get at the recognition at the world level. So what they basically did, according to the author, they found that fully replacing conventional building material, that is basically a building is a basic human necessity, and that is can be found all around the world. With the storing alternatives, new infrastructure that can build that can store up to 16.6 plus minus 2.8 billion tons of carbon dioxide, which is around 50% of 2021 and basically in 2021 there was a COVID, and because of the COVID, carbon dioxide emission was less. And then we also have another strong message from here. This paper is published in 2025, but this data contain up to 2021. It means that the high quality research often need a longer time for its publication. So we have to be very patient and we have to do lots of research for the reproducibility point of view and some others. And after that, we can get actually, this is not impossible, but it's difficult. If we can do it, of course, we can go for high impactful journals. Secondly, I want to introduce the introduction of this paper. Basically, nowadays we all are sitting here every week. This is the agenda to have an awareness in the education for developing countries and developed countries to collaborate with each other to get the net carbon emissions. This is also our goal, and many organizations are working at that because of the rising temperature and climate change and global warming. This is a serious issue of nowadays. So they address this issue, and then what's their key finding? Like if they replace, we normally we use a cement as a binder in our building materials. So if they replace this building materials with some modified materials that can capture maybe more than 50%, this basically will help us to get the carbon neutrality in the second half of this century. And then what is the relevancy? So this is basically sustainable and viable because especially in the Asia and also in the world, the population is increasing. So with the increasing population, we need more homes for living. As we need more homes, so we have to construct new buildings, and then it can be increased. Like as the building will increase, it will carbon capture capacity will increase it, and then it can last for the longer time. So this is one of the most important point here. So we can consider it. And then there is a material assessed for the carbon storage. I will show you the result because as we know that for nature and science there is a less research but a lots of discussions. So basically I want to try to make a clear concept like how they did this work. So basically uh, for building materials we are using the concrete materials, bricks, and sometimes we use some other materials made of wooden bricks and some other kind of, but they are very in less quantity. And we use as a binder material that's we call Portland cement. And this is worldwide recognized and we use it. And this is basically calcium oxide and then with the aluminum silicate and calcium and magnesium. So basically when we have a in this industrial purposes, when we prepare a cement, we have a calcium carbonate. From calcium carbonate we calcine it and that emit carbon dioxide. So this is also the biggest source of carbon dioxide. So if we use this cement with some other material that do not emit the carbon dioxide, that may be also the beneficial. So if we replace bricks, if we do not use this bricks, then we can save up to 2 gigaton carbon dioxide per year with the biomass fibers and mineral carbonate. So instead of bricks, we can use a biomass fiber and some mineral carbonation, and that can be useful for us. And secondly, we have a bio-based plastics. For a bio-based plastic, if we can use a high storage per that has a high storage per kilogram, and that can also be used as a binding material and also can be used as a bricks, and that can basically that can cut off the CO2 emission because of the cement formation. And secondly, that can absorb the carbon dioxide from the environment directly and convert it and store it for the longer time. This is also beneficial for us. And then there is a wood. We can use also wood. There are many organizations and research groups that are working on the wood base. So wood can also be used as a carbon capturing source, and basically it has a huge carbon capturing capacity in the form of biochar and some others. And we can also use the asphalt. Basically asphalt that can be this is basically achieved from the residue from the fossil fuels, and also we can use from the many industrial waste from the furnaces and other stuffs. What is the key mechanism? So what they have developed the bio materials. So by if they mix a biochar in the cement, then it can capture 0.9 kilogram of carbon dioxide per kg of the binder. So if we use 100 ton of our material in the construction industry, so that can capture around 90 ton of the carbon dioxide from the environment while they are exist in the buildings. And then we can use mineral carbonate. We can use a magnesium oxide and calcium oxide. This is a cement, and that basically can capture CO2, and then it can go to magnesium carbonate and calcium carbonate, and it can keep the carbon dioxide for a longer time. And then biogenic carbon uptake hai, and this is basically biomass derived. We can use fiber and biochar. So if we're talking about the biochar and fiber, so in the US, in the Europe, in also in the Asia, so we have many crop waste that can be utilized basically for a biochar productions, and then this biochar can be used as a material for the construction in the construction industry. So basically, this will help us in a dual manners. One, it can help us in the management of this waste material, and secondly, it can help us. And then this. building materials basically that can contain basically for long decades. Like the lifetime of the buildings is usually in the decades, like 50 years or 100 years. So they can store carbon dioxide for longer time. Even after the its expiry. So this building material can are in the solid form, and they can be basically buried into the soil and the earth. That can maybe for the long lasting solution for the carbon dioxide capturing and storage. Instead of current method that we are using, the geological rock formation, where we insert carbon dioxide at a high pressure, that has a problematic of leakage. We have terrestrial carbon dioxide storage, and we also have some ocean-based like carbon dioxide storage, but it again has a long issue for the long term. It's like it can be converted again into the and it can be emitted into the environment. So this is also problematic for us. So what will be the global impact? So if we use this kind of biomass materials, fiber materials, and other materials for the capturing of carbon dioxide as a building materials, basically, this will be the full transition by 2025, and that can have a capacity to store 1,380 gigaton carbon dioxide by 2020, by 21st century. So basically, if we have a 37 or 40 gigaton per year emission, so it has a huge capacity to store this carbon dioxide, and it can be a sustainable solution. And then it can meet our target of 1.5 degrees C rise of temperature or 2 degrees C rise of temperature in 21st to 22nd century. So we have to keep it at our minimum level. So it may be helpful for whole world. So it reduces the dependency on geological, terrestrial, and ocean storage that is already in commercialization process, but it has challenges of leakages and monitoring for a long time. And it also supports a localized resources utilization, and of course with the a new area like that cement industry and some other metal industry can use this kind of technologies, and they can also create some jobs, and it may be beneficial for the humanity as well. So basically, what will be the challenging? So challenging will be like energy demands for new materials. Of course, we have to develop them, and accessibility of the mineral and biomass resources. And then there may be the price competition, because this may be the expensive as compared to the others. So there may be some policy making and some other organizational and government level help should be given to that. Either it should be from the end user, from the builder, or it should be given to the industrialist that maybe can commercialize this kind of technologies. So what basically we have to do it basically according to this research. So they also work on the policy makings and also for the suggestions for the government level. So energy efficient carbonation process, if we want to apply it, that may be for long-term durability. So incentives should be given, because we already have a carbon credit system in the world, like how much CO2 can be emitted by the world. And if we have a plus carbon, like if we want to emit extra CO2, we have to pay the money, and that's the country which will emit and which has a surplus carbon credit, so it can sell. So that can be basically communicated through this platform. So basically, what is the result? So after this long discussions, so the summary of that discussion may be we have a like for bricks that is from the clay, and we have a cement that is a Portland cement that can be that is basically produced through the minerals calcination process that emits carbon dioxide. So if we do not use a Portland cement, so we can cut off the CO2 emission through the cement preparation, and then the other material that we have a biomass and renewable energy based materials that can be used there, and it will cut off the 2 to 5% of the CO2 emission that comes from the cement industry, and then it can capture the carbon dioxide from the environment to help us to get a overall carbon neutrality. So if we have a carbonatable cement, basically we use if calcium oxide and magnesium oxide that is basically beneath the soil in the almost in the inner soil, like 100 200 meter inside the soil. So that can be taken out from there, magnesium oxide, calcium oxide, in this kind of oxide, and this is basically carbonatable. And then it can be carbonated to capture carbon dioxide, and it can capture 0.2 to 0.5 kilogram of carbon dioxide per kg. And then we have a carbonate based aggregates like we can collect from the coal ash, biomass ash, some industrial waste, so biomass based ash. And so this material can be basically used, and that can capture carbon dioxide up to 5 kilogram per carbon dioxide per kg. And second option, maybe we can use a biochar based cement, and this basically can act as a filler and as a binder, and this basically can capture carbon dioxide more than 3 kilogram of carbon dioxide per kilogram, because usually biochar is a nanomaterial and it has a high surface area, and it can capture carbon dioxide from the environment in a maximum quantity. So is and then we have a wood. So wood based we can also use. We can also use a bio-based plastic that's been already been in use, like rubbers from the plant waste, and we also have a bio-based plastics. And then this can be used in the building materials as a coating, sometimes as a filler, sometimes as a binder. So this can also capture. And then we have this portlandite bricks. This is also calcined one, basically, that can capture carbon dioxide. And we have a biomass fiber-based bricks, and we also have biomass-based asphalt and bitumens. So this can also be these kind of materials can be replaced in the construction industry, and that can basically capture carbon dioxide from the environment. So basically, if we see the global production from there, so basically, see we are working on the concrete aggregate, and also some amount of the asphalt is there, but we are not using some other materials. So they are very in a less quantity. So if we can increase their quantity, so maybe we can get the carbon neutrality in a very efficient and in a sustainable manner. So here, this is a comparison table. So global material production is this. So basically, we need 32 gigaton per year. And then currently, so the carbon capturing material is only wood, and we also have a 2.3, and then cement basically emit 1.7 gigaton of carbon dioxide. So if we eliminate this one, and then CO2 emission will be reduced, and this can capture it, and we can increase wood base, we can increase plastic base and asphalt base, and this cement filler that is biomass base. So basically this will be the carbon negative, so we can get overall carbon negative, and we can basically that CO2 emission, which is around 37 gigatons, so that we can basically capture from there. And then basically this is the storage potential. So basically, if we use a concrete aggregate, so this can capture 10 gigaton, asphalt 1 gigaton, cement 1.3, cement filler, bricks, woods. So this all material can capture, basically has a capacity to capture carbon dioxide from the environment, and totally it can go up to 16.6 gigaton. So this is basically already a breakthrough study published in Science, that this may have a viable solution. This has a basically viable and sustainable solution for the decarbonization of this world. And then if we talk about the trends in the next century, so how we can get the things together. So this is cumulative carbon storage by 21st century and this axis. So currently we have 100% implementation of the carbon storage technologies. This one, if we apply carbon storage technologies here, so it can capture up to this 1200 gigaton from here. And if we want to attain a 1.5 degrees Celsius maintenance of the increase in the maintenance of the temperature, then we have to go about the 200 gigatons. If we want to maintain 200 degrees C, then we need a small amount, because already we have many other capture technologies. So if we think about this, so if we can go 100%, even not if here 2025 we can go 100%, and then around is it can be captured about 1200 gigatons. In 2050 it can capture 800, and so if we start application from here. So in the future, we do not need that much in the high quantity, even if less fraction is used. So that can basically capture carbon dioxide, and we can get the carbon neutrality in the next century, and we can basically control the increase of temperature of 1.5 degrees C per year or 2 degrees C per year. So this is the one relationship between the or how much we can apply this materials for the carbon capturing and storage, and what will be the impact. And this is a simulation based work, and they didn't use any advanced characterization techniques, so they just calculated through simple softwares, and they also have some raw data available on this website, this data on the website, so we can download it easily. So basically, what are the key points here? So this study basically, what this study gave us a message here. So through small modifications to replacement of the materials that we are already been used, if we replace them some modified materials, and we can go to the industrial level application, so it can capture basically 50% of the carbon dioxide emissions. So concrete can go 11.5%, bricks 2 gigatons, and wood 0.45 half gigaton. So even if we can apply bricks and our concrete and aggregates, so that can contribute basically significantly, even we do not go for the woods, because woods belongs to the plant based and trees based, and this is basically carbon capturing source. So if we do not go by this way, so basically they have a around 1.4 around 1400 gigaton of carbon dioxide capture capacity by 21st century. This is basically more than enough to attain the carbon neutrality, because 50% CO2 emission will be captured by this material. And then we have forest and other plants. We also have a CO2 conversion setups. So if we apply this technique, so maybe we can get the carbon neutrality in the next half century. So, and now basically based on this, basically this is a preliminary study, and of course, as we know, all the first time a new concept is invented and they are published in Nature and Science, and then people are trying to investigate in this direction. So if we think about this direction, maybe we can add a part of this in our introduction papers, in our fields, and we can go for some theoretical studies, and we can if someone interested in this research, so they can continue it. Like, if we assume that building materials have negligible use phase emissions, as this material likely landfill. So after we demolish this and we have a landfill, so basically someone can think like this. So CO2 can be emitted from there again, because there is anaerobic conditions in the soil. So again, calcium carbonate or magnesium carbonate can be converted into magnesium oxide, and magnesium and calcium oxide and CO2 can be emitted. This is also one important point that we can be considered for a future research. And also we can go through demolishing process, because when we demolish the buildings, so it also need a proper techniques. So we have to demolish them, and then uh, proper we can bury the materials in the landfills and in other sites that may not cause the CO2 emissions. So this may be the future direction. So we can think about the real-time application, because this is a concept. So and calculation based. So if we go to the real time, so this may be the challenging and other major challenges, as we all know. So in my personal opinion, so because these bricks like Portland cement and clay-based bricks, they are very strong mechanical strength. So if we use a biomass based and filler based, and this, so they maybe is not stronger enough to have a high rise buildings. So this will be also be the one of the biggest challenge. So that may be our future research direction, to work about to increase the mechanical strength of these materials. So if we go to the sophisticated materials like graphene, they are very expensive, although they have enough mechanical strength. But if we use ordinary biochar, so biochar basically a porous material, so there may be a problem of mechanical strength. But as per now, so it can be used as a surface in the floors, in the paint, and somehow in the outer surfaces. and as a filler, so where there is not a mechanical stance, so in that space maybe we can use it. But other than that, there is a future directions and concerns, so this is a matter of discussion. So many others publications can be done in this area, and investigators and researchers may think about these directions. Thank you so much. This is from my side. So if now the house is open for questions and answers, so maybe you can discuss again. Thank you so much.